Okay. I figured I'd give you a diode to look at, a diode in action. Have any of you ever looked at an LED when it's on? Yeah, it hurts. So, so what I did was our instructional support staff, they basically rigged up a very simple circuit. It's actually sketched on the back here. It's just a 9-volt battery. And it has a 2 kilo ohm resistor, and it has 250 kilo ohm potentiometer, so you can adjust the resistance between 0 and 250 kilo ohms. And I guess we have no pen. All right. So basically, we can plug in a diode in series with these resistors and control current. So the current is on the order of a few milliamps. Let's see. It can be anywhere from about 30 microamps up to 3 milliamps in this little thing that I'm going to pass around. So typically, yeah, in a flashlight or any other LED light bulb, it's too bright for you to look at. But if you want to take a look, I guess I should plug in an LED. I think it fell out. All right. What color would you like, red or blue? Blue. Blue? OK, that's more expensive. It's like 3 times more expensive. All right, we'll plug in a blue one. So basically, you push the red button to turn it on, and you turn the knob on the side to adjust the brightness so you can see it. OK, I have to orient it properly. For a diode, it's designed to flow current one way, so it matters like which way you plug it in. That's why I had to check. OK, yeah, so this is a blue diode, and you can turn down intensity so you can take a look. But where? OK, I thought I had a little magnifying. Oh, yeah. OK, so you can take a look. It's basically, a diode is is on the order of a millimeter squared. So it's hard to see. So you might want to take a look. All right. Just to give you an idea, so a normal diode, less than 1 square millimeter is conducting milliamps, at the most 10 milliamps, so it's too bright. But here in this little thing, you can turn it down. But it gives you an idea, like typically what the current density is in a light-emitting diode. OK. So last time we covered the basics of current flow in a diode as a function of the applied voltage. So I sort of forgot to go back to this little demo online, and want to get back to it. So remember this. There are 2 ways that current can flow in a semiconductor, due to diffusion or drift. So due to the difference in concentrations of electrons and holes on either side of the junction, there's a concentration gradient. So you'll end up with diffusion current, so electrons into the p side and holes into the n side. And then you also have, due to this built-in electric field that counteracts diffusion, you'll have drift in the opposite direction. So electrons will want to drift back to the heavily doped n side, and holes will want to float back to the p side. Now, what happens when you apply a forward bias is that you reduce this potential barrier, so exponentially more carriers can diffuse and have enough thermal energy, have enough kinetic energy to go across the junction because they can overcome that potential barrier. So exponentially have a lot more diffusion current flowing under forward bias than drift current. But once you go to reverse bias, you increase that potential barrier to diffusion, so hardly any carriers can diffuse across. The only current that's left is that little small amount of drift current due to minority carriers that happen to diffuse into the depletion region, and then they drift across. OK? So the summary from last time then, this is really what you hopefully will need to remember for the quiz or for the final exam. It's just under forward bias, you reduce the potential barrier, so you have more diffusion across the junction. Okay, so let's write this down. So you have this ideal PN junction diode current. So remind me, what does this first term represent? It's actually, OK, Ni squared times this exponential over ND, the doping, right? So Ni squared over Na times e to the QVA over kT minus 1. I mean, that's actually all included in this first term. Okay, so what does that first term correspond to? Electrons, right? So it's diffusion of electrons within the quasi-neutral p region, right? That's why you have doping on the p side, right? The acceptor doping on the p side. You have the diffusivity of electrons on the p side for the minority carriers, and the diffusion length of electrons on the p side. Okay, so this term is associated with electron diffusion across the junction into the p region. So therefore, this term is associated with hole diffusion. So this is the holes that had enough kinetic energy to diffuse from the p side to the n side, and then they're diffusing with a diffusivity of d sub p, and they die out on average within L sub p, a distance L sub p, and their concentration is proportional to Ni squared over Nd, and it's enhanced at the edge of the depletion region exponentially. Okay? Okay, so that's under forward bias. Under reverse bias, as I towards the end of the last lecture, one way if you can think of the reverse bias current that flows is just the current that flows that's supplied by the rate at which minority carriers are generated within one diffusion length of the depletion region. Right? So only the carriers, this sort of simple depletion approximation, only this concentration of carriers, well, let's see, only the carriers that are generated within one diffusion length, within one minority carrier lifetime, can diffuse into the depletion region before recombining. Okay, so if you look at this, basically you're looking at the concentration. So this is the generation rate, right? So it's concentration per unit time, but then you have to multiply the concentration by the volume, right? So what is the volume of this region there? That's equal to the diffusion length, minority carrier diffusion length, times the cross-sectional area. So that's why you have A times Ln for the electrons and A times Lp for the holes, right? So you have to multiply, because this is concentration of electrons generated per unit time, but you have to multiply by the volume, and then current is due to charge flow. So, okay, so the reason why this is important is because later when we talk about light-emitting diodes, there's recombination occurring, right? So the carriers under forward bias are recombination. See, they're recombining, right? This is in the summary here, right? So recombination occurs primarily in the quasi-neutral regions, and when electron and hole pair recombine in some compound semiconductor materials, a photon is given off. So that's how a light-emitting diode works. Now, a solar cell basically is just the opposite. You shine light and you generate electron-hole pairs. Okay. All right. So in a solar cell, where is most of the energy generated within the diode? Is it in the depletion region, in the quasi-neutral regions, or somewhere else? Based on what we know here. It's actually primarily within, so it's within one diffusion length of the depletion region. So if you generate electron-hole pairs within one diffusion length of the depletion region, they will diffuse to the depletion region and get swept across. So you end up generating current, negative current. Okay, so it's actually important to know where the recombination occurs under forward bias, primarily, and where the generation that matters occurs under reverse bias, because that sort of helps you understand how light-emitting diodes and solar cells work, and actually photodetectors also. Okay. Any questions left over from the last lecture? No. Okay. Let's go, and today's lecture should be actually not very long. Might not be bad. So if you have any questions related to the quiz, I'm happy to answer that at the end. Okay, so there's just two topics for today's lecture. First of all, it's a narrow-base diode, which is more realistic in an integrated circuit device. And we'll start talking about non-ideal behaviors. So the first one today will be covered is junction breakdown. Okay, so when we derived the equation for the current in an ideal diode, we actually assumed that once carriers diffuse across the junction, they become minority carriers and they die out gradually due to recombination. But that's assuming that the p-type and n-type quasi-neutral regions were really long. So there's like plenty of time or distance for carriers to diffuse before they die out. Okay? So that's why we have an exponentially decaying function for the carrier concentration. And when we take the derivative, it's also an exponentially decaying function. And that's we take the derivative to get the diffusion current. Right? So both carrier concentration and diffusion current decay exponentially. But as I've sketched many times already this semester, in a typical integrated circuit, these p-n junctions are usually not only one-sided, in that one side is much more heavily doped than the other, but also usually one side is pretty short. Okay, so certainly less than 1 micron. The n side or the p side, one of these is going to be always typically less than 1 micron long. Okay, so does anybody remember typically what a diffusion length is in moderately doped silicon? What's a typical diffusion length? Minority carrier diffusion length. Tens of something, yes. It's on the order of 10 microns. I mean, several microns or tens of microns, depending on the dopant concentration. Okay, so in reality, then, this assumption that we used to derive the ideal diode equation is not valid, at least for one side of the junction. Okay, so that's what we mean by short base or short, quasi-neutral region diode. So we have to do something special in this case. Okay, so so instead of using a boundary condition that at x is infinity, right, like far away from the depletion region, it goes to 0, we have to say that the excess minority carrier concentration actually goes to 0 at the ohmic contact. So that means, wherever we're making electrical contact to the p-n junction diode, the excess minority carrier concentration there is 0. Okay, so that's the new boundary condition that we need to use to resolve the minority carrier diffusion equation. Okay, so in the first part of this lecture, we're going to rederive the IV equation, but with only this difference, the boundary condition. Okay. So let me review this figure here. So just to review, why is the excess carrier concentration, why is it reasonable to assume that's 0 at a metal contact? Negative and positive charge. Well, okay. That's like a non-ideal case. Okay, but just ideally, just an ideal, let's say an ohmic contact. It can be a practical ohmic contact. What is the definition of an ohmic contact? I mean, like it should have low resistance, right? So basically, if you apply this voltage here, I think I'm going to have this problem all through the lecture. Okay, so if you apply a voltage across this structure, current flows, and as I said, since these regions are heavily doped, relatively low voltage will be lost across these regions. I mean, because the resistance will be low. Since the depletion region is not very electrically conductive, I mean, because it's depleted of mobile carriers, that region will look more resistive. In other words, it'll have the largest voltage drop. But look at the contact. So at the contact, we're assuming negligible voltage drop. In other words, the applied bias between the metal and the semiconductor is going to be like millivolts. Remember, we sort of derived that. It was actually in the homework. So let's say 10 millivolts compared to usually a volt at least across this diode, or on the order of a volt. So the only reason why we assume the excess carrier concentration is 0 is because we're assuming the applied bias is essentially 0 at a metal semiconductor contact. Okay, so in other words, we're assuming it's at equilibrium. Right? If the applied bias is 0, then we're at equilibrium. So that is the fundamental reason why we are making this simple, using this simple boundary condition, that the excess carrier concentration is 0 at an ohmic contact. Okay? Okay, so we reviewed now the minority carrier diffusion equation, because the drift current due to minority carriers is negligible in the doped regions. Actually, I should mention, just to be complete, so in this plot, which you're going to have to do for the homework, that's just being assigned today. Okay, so let's do it in color. This current here is whole diffusion current, right? And this current over here is electron diffusion current. Okay, so holes on the right are minority carriers, and electrons on the left are minority carriers. And remember, because this negligible voltage drop in the quasi-neutral regions, the electric field is relatively small. So if you have small electric field and small carrier concentration, then the drift current is negligible. And that's why we can use the minority carrier diffusion equations in these quasi-neutral regions. But if you look at the electron current on the n side, this current here has both diffusion and drift components. Okay, so for the majority carriers, drift current is actually not negligible, because even though the electric field is small, the carrier concentration is large. Okay, so drift current actually can be significant. So the majority carrier current actually starts out as drift and diffusion, and only after it crosses the junction, it becomes only diffusion current. Okay? All right, so that was like one detail you probably should know. Okay, so coming back, so now we're again talking about minority carriers in the quasi-neutral region, so we only have to worry about diffusion current. So here's the minority carrier diffusion. So now we're starting on the n side. The minority carrier diffusion equation, so that means for excess holes on the n side, this is just setting in steady state. So the derivative with respect to time is 0, and then you can actually rearrange the minority carrier diffusion equation to get this second order differential equation at the upper right here. Okay? So again, we assume this convenient coordinate system where we define x prime to be 0, okay, at the edge of the depletion region, just like before. And so now we can just write, so we know that if the concentration of excess carriers is, or the derivative, the second derivative is proportional to the concentration of excess carriers, then we know it has to be some kind of exponential function. So either exponentially increasing or exponentially decreasing with distance into the quasi-neutral region. So the general solution has two terms, and we have to solve for A1 and A2 by applying two boundary conditions. So the first boundary condition, this is set by the law of the junction that we described last time. Right? So the excess carrier concentration at the edge of the depletion region is enhanced by this exponential factor. Sorry, the minority carrier concentration is enhanced exponentially. So the excess minority carrier concentration is equal to the equilibrium value times this exponential factor minus 1, right? Because this is the excess carrier concentration. So that's why you have this minus 1 there. Okay, so that's one boundary condition that's set by the voltage applied across the junction. And then the second boundary condition now, rather than saying x prime is infinity when it goes to 0, now we say x prime is just equal to x sub c prime. So this is basically, this is just where the location of the metal contact is. Okay, so if you go ahead and write the equations, so at x prime equals 0, if x prime equals 0, those exponential terms go to 1, so you just have A1 plus A2. We know that that has to equal the excess carrier concentration at the edge of the depletion region. So that's one equation. And then the second equation, you have to plug in xc prime rather than infinity, right? And then now that, in that particular case of x prime, that has to equal 0. So it turns out then, if you solve these two equations for two unknowns, you can get this expression for the excess carrier concentration as a function of distance. Okay, so this still looks familiar, right? It starts at some maximum, and it's going to look like this. So here's x prime, and so that's equal to x equals 0, right? X equals xn. So the excess hole concentration on the n side is going to look something. Okay, it depends. Okay, it's going to basically it's going to look something like that. Okay. All right, but the key is the value at the edge of the depletion region is still the same. So it's still Ni squared over Nd times this exponential factor -1, because we're talking about the excess minority carrier concentration now. Okay, but it goes to 0 at xc prime. Okay? That's it. Okay. So physically, well, okay, we'll come back to physically what's going on. But we're going to come back to this in like 2 slides. But if we are only interested to derive the IV diode equation, then all we have to do, we don't care about what it looks like. We just do the math, take the derivative to find the diffusion current at the edge of the depletion region. So now we have an expression for delta p sub n as a function of x, and we can take the derivative with respect to x or x prime and multiply by dp and minus q. We do that on this slide. Okay. So we have this exponential of something over some positive number minus exponential of the same negative number. So it's just convenient to write it more compactly as hyperbolic sine. Okay, so it's just a ratio of hyperbolic sine functions. So just to remind you that the definition of hyperbolic sine is shown here. All right, so it's just notation, right? It's just more compact. I guess it's easier to write hyperbolic sine than exponential, plus and minus. Okay, so when you take the derivative, then you get actually a hyperbolic cosine on the numerator. You still have a hyperbolic sine on the denominator. Okay, and the hyperbolic cosine is defined right there. Okay, so we take the derivative of the excess minority carrier concentration. That gives us the diffusion current as a function of distance. But we really don't care what it looks like necessarily with a function of distance. We just want to evaluate it at the edge of the depletion region to find the diode current. So we just evaluate at x prime equals 0. Okay? So if x prime equals 0, then, okay. The hyperbolic sine, what is the hyperbolic sine of, wait a minute, x prime, oh yeah, okay. Right, so you plug in x prime is 0, and you get this expression here for the current due to holes diffusing into the n side. Okay? So that's current due to holes diffusing into the n side. Now, if that is the dominant source of current across the junction, in other words, if the p side is doped much more heavily than the n side, so that most of the current is due to hole diffusion across the junction, then that's roughly equal to your diode current right there. Okay, so that's all I'm saying here in this with this sentence here. So assuming that this is the dominant current, then we can just write a simple equation. Well, it's not that simple anymore. Okay, so it's written like this because hopefully you can recognize this first portion here. That's just pretty much the same as for the long base diode. I mean, well, for the ideal diode, right, with very long regions. Okay. All right, thanks. Okay, so the only difference is this new term over here. Okay? So what happens when this term here, x sub c, so looking at this x sub c, so that's essentially the length of the quasi-neutral n region. What happens when that quasi-neutral region becomes really long, like very long compared to the diffusion length? what does cosh go to if the argument is really, really large? It goes to, well, actually it's the ratio. Okay, so the e to the minus something, right, in the cosh in the cinch essentially goes to 0. And so you just end up with, e to the positive something over e. So basically this term becomes dominant. If this argument goes to, is very large, then this term goes, is negligible. And you just have that first term. And same thing here, this term becomes negligible and you just have that first term. So what does this fraction go to if, very good. So approaches 1 if xc prime is much, much greater than LP. Okay, so that's one extreme. In other words, yes, you get the long base diode equation or expression as you should if the quasi-neutral region is much, much longer than the diffusion length, minority carrier diffusion length. Now, what is the other extreme? The other extreme is if that argument is really, really small, like much smaller than 1. So that's what's shown here. Just this hyperbolic sign approaches the argument. The value of the hyperbolic sign approaches the argument if the argument is really small. And for a hyperbolic cosine, it actually approaches 1. Well, or 1 plus the argument squared. But anyway, if this is really small compared to 1, then it's roughly 1. Okay? So if we actually take the other extreme, now that the length of the quasi-neutral n region is much smaller than the minority carrier diffusion length, the other extreme is that that ratio becomes LP over XC prime. Okay? So we plug that in here. Notice the LPs cancel out. And so what you ended up with is something that kind of looks like the ideal diode equation, except rather than the minority carrier diffusion length, you have the length of the quasi-neutral region. That's it. So I hope that's pretty simple, right? So you actually can just remember the same equation, but now the slope is not dictated by this exponentially decaying function. It's actually dictated by the width of that quasi-neutral region. And the reason for that is because you're decaying essentially from the peak value at the edge of the depletion region to 0, like this, and it's close. It can look like a straight line if this quasi-neutral region is very short. Okay. Now, as I denoted here, one characteristic of a straight line is that the slope is constant. Okay. So if a slope is constant, so if the slope of this line is constant, well, the derivative is constant, what does the derivative of the carrier concentration give us? Diffusion current, right? So that means the diffusion current is constant. So in other words, whatever whole current flows at the edge of the depletion region, it will also flow at the contact. In other words, you will not lose any whole current due to recombination in the quasi-neutral region. Or in other words, no holes recombine with majority carriers. Does that make sense? Because it's too short. Like you make it to the contact before you even have a chance to recombine with the electron. Right? So if the quasi-neutral region is too short, the chances of being recombined before you reach the contact are 0. So you basically have a straight line, constant current. The current is the same at the edge of the depletion region as at the contact for the minority carriers. Does that make sense qualitatively? Yeah.
So that means the holes don't recombine.
That's right. So we had already assumed ideally that there's no recombination in the depletion region, but we already hinted yesterday that in reality there's always a little bit of recombination. But yes, so for the ideal diode equation, we assumed no recombination to begin with in the depletion region. And now for ideal short base diode, there's actually also no recombination in the quasi-neutral region. That's right. Okay. So then what does, so remember we saw, okay, let's go back to the ideal diode, lecture 10, right here. Remember for the ideal diode, yes, we had constant current in the depletion region because we're not losing any carriers, due to recombination as they flow across the depletion region. But then once they reach this quasi-neutral region, they die out due to recombination. So now, if these quasi-neutral regions are really short, they don't die out. In other words, the current stays constant. So whatever current made it across the depletion region is going to continue to flow and reach the contact on the N side. Now what I've drawn here is a case for both short P side and short N side. Okay? So how would it change if only one side is short? It would decay on the long side, right? So which side do you want me to make long, just for example? P side? Okay. So let's say the P side is long. And okay, so it's long is all relative, right? So remember, long relative to what? Diffusion length. But okay, on the P side, it's the diffusion length for what? Electrons or holes? Electrons. Very good. Okay, so where is that? Okay, so it would look like this for electrons if the P side were long. So long P side. Okay, so electrons, when they diffuse across a junction due to the concentration gradient, they will still die out with distance, within a few diffusion lengths. Okay, so that's not completely correct. What else do I need to change on that plot? JP. Well, actually, or J, but okay. JP, because the sum of Jn and Jp always has to equal J at every point in the diode. So in order for this to be accurate, it has to look something, oops, wait, complementary, exactly, complementary, so the sum always totals up to J. Okay, so if I were to show you a plot of current components, whole current and electron current at different parts of the diode, you should be able to tell me if it's a long base diode or short base diode, and which side is more heavily doped, right? Like in this example, which side is, did I tell you the answer here? No. Okay, which side is more heavily doped in this example? P side. Right, very good. Okay, because the current diffusing across the junction is dominated by hole diffusion compared to electron diffusion. Very good. Okay, so the ideal diode equation, all you have to do is modify, instead of the denominator, instead of L sub P or L sub N, right, the minority carrier diffusion length, you just have to put the length of the quasi-neutral region. Okay? So remember, this is just the slope, right? The longer the diffusion length, the longer it'll take for it to die out, so it's less shallow of a slope. Same thing here. If it's a short base diode, the longer the width of the quasi-neutral region, the more distance you have to die out to 0. So the slope will also be smaller, right? So hopefully that makes sense qualitatively. Okay. Any questions about narrow base diode? Yes, Josh. Typical. Okay, so the question was, what is a typical width? Okay, so in a modern integrated circuit, these junction depths are typically less than 1/10 of a micron now, the shallowest, in the shallowest regions. So it certainly is less than a micron on one side, typically in a one-sided p-n junction. And it can be as short as less than 1/10 of a micron. And in fact, that is a problem because, okay, I'm going to draw this MOSFET again. So as we scale down, as we miniaturize the transistor, we're scaling down the lateral dimensions. And in order to have it work properly, we actually also have to scale down the vertical dimensions of a transistor. That means we have to scale down the junction depth. Okay? And actually, when a transistor is like, made like, we actually want a transistor to have current flowing between these doped source and drain regions. We actually don't want current flowing like in this diode over here. Okay, it's just the diode is kind of like a parasitic device that exists here. Okay, but what happens? What happens to this current? Let's see. So what happens to this factor if we make this junction shallower and shallower. In other words, we're making the quasi-neutral region shorter and shorter. What happens to the current? Increases. So in other words, the reverse bias, so usually in a transistor, this junction here, this drain junction is reverse biased, and we don't want, significant reverse bias current to flow. So if we make the junctions too shallow because we're trying to make the transistors too small, actually the leakage current, the reverse bias, undesirable leakage current, or reverse bias current of the diode can actually become a problem, right? So we actually can't, so there's some practical challenges scaling transistors that you can't really arbitrarily scale the depth or the length of these p-n junction diodes very aggressively. Okay, so that is a practical issue nowadays with modern CMOS devices. Okay, so that's just a summary for your information. So just remember, the shorter that quasi-neutral region, the steeper this concentration gradient, right? Because it goes at the edge of the depletion region, that concentration is dictated by the voltage applied and by the doping concentration. Okay, that concentration at the edge of the depletion region does not depend on the width of your quasi-neutral region. So as you make the diode shorter and shorter on one side, basically you're making it go, the excess carrier concentration go to 0 sooner and sooner, and you make a steeper and steeper slope in the concentration, so you have more and more diffusion current. Okay? All right, any questions about the narrow base diode? Nope. Okay, so the first non-ideal behavior we'll cover today, and then that'll be a break, is the breakdown. Now, breakdown doesn't sound very good, but that's what we call it. This is what happens if you apply too large of a reverse bias on your diode. Ideally, in reverse bias, you just have this, drift current due to minority carrier generation within a diffusion length of the depletion region. But it turns out if you apply too large of a reverse bias, then at some point you can suddenly start to conduct a lot of current. And in fact, that current can turn on in the negative direction much more abruptly than in the forward direction. Now, for some circuit applications, it's nice to have this kind of a device where it's designed, so this diode symbol is actually showing, this device, this Zener diode, is designed to turn on with current flowing in the reverse direction. Okay, but the purpose of this diode here is to start conducting a lot of current if the voltage provided to this integrated circuit starts to exceed 3.7 volts. Okay? In other words, you're protecting this integrated circuit from voltages, anything from having a voltage above 3.7 volts. Because once the circuit starts to want to go above 3.7 volts, this diode starts to conduct a lot of current, get voltage dropped, and basically you'll never be able to apply more than 3.7 volts to that IC. So you protect the IC. Okay, so can somebody maybe suggest, well, why would we want to use a Zener diode rather than like a normal diode? I mean, why wouldn't we want to just, use a normal diode, put a diode like this, and not force it to operate in breakdown, but just, have a diode like this to protect the integrated circuit? Yes. That's right. So, yeah, the typical voltage you need to apply across a silicon p-n junction diode is like less than 1 volt, and then it'll start to conduct a lot of current. So a lot of times you might want to apply more than 1 volt to your integrated circuit. So you only want this diode to conduct current at some higher voltage. So you're right. That's exactly right. The Zener diode, you can actually tune, or you can buy a Zener diode from a wide range of breakdown voltages. So you can actually have breakdown voltages, well above 1 volt. It could be 10 volts, 20 volts. I mean, it could be 100 volts. Okay, so that's why it's more versatile when it's operated this way, and also it turns on more abruptly. So it's not like gradually turning on as the voltage here gets close to the forward voltage. That's right. Okay, so let's study this phenomenon. So first of all, we want to come up with an expression for the breakdown voltage. Okay, so the breakdown voltage, well, the reason why the diode breaks down, and this is not a catastrophic thing, it just starts to conduct a lot of current. It doesn't block the current well anymore, and I'll explain why. But so it's not like destroying the device. So the diode can actually turn, go back and forth along this current versus voltage characteristic. You can change the voltage back and forth. It's not going to break it. It'll be just fine. Okay, so the key thing that you need to know is that basically this phenomenon just happens if the electric field is too high in the p-n junction. Then you can start to see some non-ideal conduction occurring. So it's all related to that peak electric field at the junction. So remember, we derived the electric field distribution, so electric field as a function of distance, by integrating the charge density. Right? So we integrated the charge density so that the slope here, the derivative of the electric field with respect to distance, is equal to the charge density scaled by the dielectric permittivity of the semiconductor. Okay, so this is QND over epsilon s on the right. And then on the p side, the charge density is negative, right? The acceptors are negatively charged. So the slope here is minus QNA over epsilon s. And at the junction, the electric field is continuous. Okay, and then just to review, what does the area under this curve represent? The magnitude of the total voltage drop across the junction. That's right, the total voltage drop across the junction. Great. Okay, so if we want to increase the total voltage drop across the junction, that means we have to apply a reverse bias, okay, negative VA. That will, so how would this curve change? Let's see. Somebody want to remind me? If we want, if the black represents like some reverse applied bias, how would the curve change if we increase that reverse bias, the magnitude of the reverse bias? It'll get wider, right? The depletion region. Okay. So remind me. I think on the homework the reader was saying is wrong. Okay. So let me ask. Right. What matters is we want to increase the total voltage drop across the junction. So we want to increase the total area under this curve, right? So I could increase the total area under this curve by drawing that. Okay. Now tell me why that's wrong. Slope. That's right. The slope is not right, because the slope is dictated by the doping. And I'm changing the slope here. I don't want to see that on anybody's quiz. Okay, all right. But apparently on the homework, some people did that. Okay, so the correct way, if we increase, okay, if I can draw this properly. If we increase the reverse bias, then this is what happens, right? The slope is the same on both sides. It's just that the depletion width widens, okay? In order for the total area to increase to support a larger voltage drop. So remember, this VA is negative, is what we're looking at. We're considering that now, okay? Okay, so this is actually the full equation for the peak electric field at 0. And for a one-sided junction, if NA is much greater than ND, or ND is much greater than NA, this fraction there, we just have to, it just reduces to the dopant concentration that is, which one? The higher dopant concentration or the lower dopant concentration? Higher? Okay, let's just say let's say if NA is much, much greater than ND, then you can say, okay, this is negligible compared to NA, right? So now the NAs cancel out. So basically, you retain the term associated with the more lightly doped side. Actually, that's what I say at the bottom of the slide. All right, so here's a simple equation for the peak electric field. Notice that it depends on the doping concentration on the more lightly doped side, and it actually depends on the total voltage dropped across the junction. Okay, so what happens is that if that peak electric field exceeds some critical value, so this is a new term, electric field, critical electric field, or E sub, curly E sub CR. And typically, I'll tell you, it's on the order of close to megavolt per centimeter. Okay, so 1 volt dropped across like 10 nanometers. So if the peak electric field exceeds some critical value, then you'll start to see a lot of reverse current flowing. Okay? So we just take the equation on the previous slide and say, okay, the peak electric field is going to reach this critical value. At that point, we're breaking down. So VA is equal to minus V breakdown. When so two new terms here. So V sub BR is just a breakdown voltage, and it's negative. And E sub CR is just the critical field at which breakdown occurs. So then we can invert this equation and get an equation for a formula for the breakdown voltage. Okay? And notice that the breakdown voltage is inversely proportional to the dopant concentration on the more lightly doped side. Okay, so typically for most Zener diodes, have some breakdown voltage well above 1 volt. What is the typical built-in potential for silicon, for silicon p-n junction? It's less than 1, right? So if we're talking about designing a p-n junction diode to break down at high voltages, then this VBI term can be neglected if you know that your breakdown voltage is much greater than 1. Okay? Okay, so if avalanching is the mechanism by which current starts to flow under high electric field, then typically the breakdown voltage is much greater than 1. And so the formula for the breakdown voltage can be simplified to this equation here. Okay, so it's just the same as on the previous slide, except we've dropped off VBI because that's negligible compared to this value. Okay, so this is a little bit of review, but under low electric field, so low reverse bias, we have carriers that minority carriers diffuse into the depletion region, and then they drift across. Okay, so that's electrons from the P side, and and if they're holes, then they're holes from the N side. And by the way, okay, so remember that the typical, okay, what is the typical depletion width? Just typical. On the order of a micrometer, or tenths of micrometers, okay? And what's a typical mean free scattering or mean free path between scattering events? 10 nanometers. So that's much smaller than the depletion width, right? So that means typically a carrier, when it drifts across the depletion region, will scatter many times. So that's why it's illustrated here. You're going to scatter. You're going to have a scattering event where you lose some kinetic energy, and then you get accelerated by electric field again to gain kinetic energy, but then you scatter and lose that kinetic energy. So this is how drift occurs in a semiconductor, and that's why when you lose that energy, where does it go to with each scattering event? To the lattice. And that's why we have heating, right? Joule heating. When you flow current through some material, you heat it up, right? This is basically due to energy lost by scattering to the lattice. Okay, so that's what happens under low electric field. This energy that is lost by an electron or by a hole whenever it scatters is relatively small. But if you have high electric field, so you have really large voltage, actually, okay, so let's review. What is that distance there? QVA, excellent. This is actually the magnitude of QVA. Distances, I'll just say, are always positive. So the magnitude of the difference between the Fermi levels in the quasi-neutral P side and the quasi-neutral N side it's just QVA. So now, notice, QVA is really huge, right? So applied bias is really big. So the potential barrier to diffusion is really big. So now, again, you still scatter, roughly 10 times, or every 10 nanometers, if you're an electron or a hole flowing through the depletion region. But now, because you have higher electric field, you gain more kinetic energy between each scattering event. So when you scatter, you go to like 0 kinetic energy, you're losing more kinetic energy. And if that kinetic energy Okay, it's hard to draw it accurately because the band gap is kind of large. But that kinetic energy that you lose is ideally greater than the band gap energy, then you can actually generate an electron-hole pair upon a scattering event. Now, due to conservation of energy and conservation of momentum, it turns out that that minimum energy that you have to lose is 3/2 of the band gap energy. In the past, we've assigned that as a homework problem, but just all you need to remember is that the energy lost upon collision has to be greater than the band gap energy in order for an electron to create an electron-hole pair upon a scattering event. Okay, so then after the electron is scattered, it will continue to be accelerated by the electric field, and it'll scatter again, and then it can create another electron-hole pair. So it has maybe a dozen chances to create electron-hole pairs as it drifts across the depletion region. Okay, but what happens to those electrons and holes that are generated along the way? They each also get accelerated by the electric field, electrons to the right and holes to the left. So each electron and hole that is generated can itself go on to generate electron-hole pairs. So this is that's why it's called avalanche mechanism. Basically, you end up with a whole bunch of electrons and holes that are generated as electrons and holes drift across the depletion region. So you end up with lots of negative current, right? Because you have electrons flowing to the right, that's negative current. Holes, positive charge moving to the left, that's also negative current. You end up with a lot of, suddenly, once the electric field is large enough to cause electron-hole pair generation upon scattering, you can get a lot of current to flow, negative current to flow. For this breakdown mechanism, electric field has to be in the range of mid 10 to the 5 volts per centimeter. Okay, you could probably, if we wanted to, we could do that. Let's do that since we have some time. Okay, so let's say, remember the average distance between scattering events is 10 nanometers. Okay, and we know that the carrier has to lose how many electron volts? Let's make it easy. Let's say one. Let's say 1 electron volt. Okay. So that's equal. So that the Q. Yeah. Okay. So 1 electron volt. So what? So remember, the electric field is equal to the derivative of the conduction band edge, right? Okay. So basically, how steep is this? So this corresponds to, oops, sorry, it's 1 over Q, right? So this is basically 1 over 10 to the minus 6. Is that right? So yeah, it's 10 megavolts per centimeter. Does that make sense? Right, so that gives you order of magnitude. So yeah, that's basically, that's order of magnitude. On the order of just under a megavolt per centimeter is needed to see this avalanche breakdown occurring. I think it's a megavolt. 1 volt, okay, 1 volt over 10 nanometers. A nanometer is 10 to the minus 7 centimeters. Yeah, okay. Okay, so it turns out that the breakdown, okay, looking at this, I know this is kind of hard to read, but depending on the dopant concentration on the lightly doped side. Okay, so why does it matter on the lightly doped side? Okay, yeah, why is it the electric field on the lightly doped side that matters more? Well, where does most of the depletion region reside? On the lightly doped side, right? Okay, so depending on the dopant concentration on the lightly doped side, if the dopant concentration is higher, what happens to the average scattering distance or mean free path? Right? If you have more dopant ions, then it's more likely you'll get scattering. So the average time and the average distance between scattering goes down. Okay? So if this distance here decreases I mean, in other words, the distance you have to travel before you have to lose your kinetic energy. If that distance decreases, what happens to the critical electric field? What? Oh, okay. Can somebody explain this to me? I'll give you a. You want a diode, or do you want a? Okay, do you want a pen or a pencil? This is a nice mechanical pencil. But anyway, okay. Can somebody explain to me? Okay, if we have more heavy doping, we'll scatter more often. So this distance here, instead of 10 nanometers, let's say it'll be less than 10 nanometers. So where's my pen? In order to gain 1 electron volt of kinetic energy, you need higher electric field, right? Yeah. Right. I should give myself a pen. Okay. So that's why the electric field is higher for higher doping. Right? So the critical electric field for avalanche breakdown depends on the dopant concentration. Okay, does that make sense? Pass these around, whatever. Whoever wants it. One's a pencil and one's a pen with a diode. Okay. So that's what happens if both sides are not degenerately doped. Okay, so there's some rare cases where maybe both sides are very heavily doped. Right? So even the lightly doped side is very heavily doped. So what happens to the width of the depletion region when you have both sides very heavily doped? Very small. So now, even at equilibrium, you notice that there's really not. Okay, so what's the typical width of the? Remember from the Schottky diode or practical ohmic contact? What kind of distances do you think we can have significant tunneling, quantum mechanical tunneling occurring? 10 nanometers, right? So if we have heavy doping on both sides of the junction, so the depletion width, the total depletion width is on the order of 10 nanometers or less. If we apply a little bit of bias, we actually get tunneling, right? So if the doping on both sides, both sides have to be heavily doped so that the total depletion width is narrow, you can actually get tunneling from allowed, these are allowed conduction band states into allowed valence band states to allowed conduction band states. So this is what we call band-to-band tunneling, because it's from the valence band to the conduction band for electrons, or you can think of it as holes tunneling from the conduction band to the valence band. Okay, so carriers can tunnel either way. In any case, so let's say we have electrons here that can tunnel over to the right. So that's negative current, right? Or you can have holes here tunneling to the left, and that's also negative current. So again, all you have to do is just apply a little bit of negative bias in order to line up the allowed energy levels in these two bands to allow quantum mechanical tunneling to occur. Okay, because they have to be allowed to exist on both sides of the barrier. And typically this occurs so for this to occur, you can do the calculation, I guess. So again, it turns out, what is the total, this is really rough numbers. What is this total barrier height? Yeah, so about 1 eV, right? Just very roughly, is 1 eV. And like I said, the tunneling distance has to be on the order of 10 nanometers or less, right? So that means, again, so the critical electric field is greater than a megavolt per centimeter. Okay, so if you dope both sides of the junction very heavily, then you can get this to occur as well as avalanche breakdown. But this will become more and more dominant as you dope the junction more and more heavily, on both sides. Okay, so you don't really need much voltage here to be applied in order for tunneling to occur, right? Because as long as you have enough voltage to lower this conduction band below this valence band, you'll allow energy states to line up and tunnel. Okay, so one way to distinguish whether a p-n junction is breaking down due to tunneling versus avalanche is to just simply look at the magnitude of the breakdown voltage. Okay, so in this regime here, breakdown is dominated. The most dominant breakdown mechanism is avalanche. Okay. So this is a plot of the breakdown voltage on a logarithmic scale versus dopant concentration on a logarithmic scale. So this is dopant concentration on the lightly doped side of the junction. Okay, so if the breakdown voltage is like many volts or tens of volts or hundreds of volts even, then it's very likely that the dominant mechanism for breakdown is avalanche. Okay, because the width of the depletion region is not going to be small enough to allow for significant quantum mechanical tunneling. So only below this dashed line will Zener or tunneling, Zener breakdown or tunneling mechanism becomes dominant. Okay, because both mechanisms can occur at the same time. It's just a matter of which one's going to be more significant. Okay. So these are curves for different semiconductor materials. Gallium arsenide, forgot the band gap energy. Hey, Peng, do you remember the band gap energy for gallium arsenide? It was on a previous. 1.6? Okay. I know it's greater than silicon. Okay. And at least I know germanium, 0.67 eV. Okay, so here's germanium. These are the band gap energies. And silicon, yes, I remember that. Okay, right, so if you have a larger band gap, you need to lose more kinetic energy to generate electron hole pairs. And so it's harder to break down a wide band gap material. Also, even if you heavily dope it, the height of this barrier actually also, well, yeah, okay, so if you have a larger band gap, it turns out you need a large electric field also to get tunneling to occur, to get those valence band states to line up with the conduction band states. So just generally then, you need more voltage to break down a large band gap p-n junction. And germanium, on the other hand, has a smaller band gap, so it's easier to break down a germanium p-n junction diode. Okay. So actually, that's not a good thing. Remember, okay, do you remember which one of these? Germanium actually is interesting because it has higher electron and hole mobility than silicon. So for transistor application, actually germanium is a better material. But one of the reasons why germanium isn't desired, is not used, is one of many reasons, is that, well, you're going to have leakier p-n junctions. They'll break down more easily. There are a lot of other problems with germanium. Okay. All right. Any questions just qualitatively about breakdown versus doping? Yes. NB. NB? Oh, okay. So this is a sort of an empirical fit. Okay, so NB is just NA or ND. So this is just showing empirically they find that the slope of this dopant dependence is -3 quarters. Yeah, so that's just empirical. That's all it is. It's just if you want to like model this like for, I don't know, some circuit, if you want to predict some circuit performance, how the breakdown voltage will change with doping, you can use that curve. So remember at the very beginning, so not the very beginning here, right? For various Zener diode applications, we'd like to be able to say, okay, maybe set the voltage, the protection voltage level, right? So we can do that by picking a Zener diode with the appropriate doping, right? So we can basically, as you see from this chart, the breakdown voltage can vary over orders of magnitude. Yes, Josh. Okay, so the question is, do we destroy the diode? So typically, no. Basically, just a lot of current can flow by avalanche, and because you're generating electron hole pairs, so you're not going to catastrophically like heat up the diode. But eventually, yes, if you conduct too much current through the diode, then you will heat it up, and it can start to get damaged. But typically, when you use a Zener diode, you purposely want current to flow once in a while here, and it will not destroy it. Yeah, it's not catastrophic. Yeah, so it's maybe not a great name to call it breakdown. Okay. Okay, so one way, as I said, to tell whether or not there's avalanching or tunneling that's dominant under breakdown is to look at the magnitude of the breakdown voltage. And finally, for the last slide, another way is to look at the temperature dependence. So you can heat up or cool down your diode and see if the breakdown voltage, how it breakdown voltage changes. Okay? So let's first look at the avalanche mechanism. Well, I already put the answer up there. Okay. So if the breakdown voltage gets higher, that means it's harder to break down your diode, right? So why does it become harder to break down your diode if you increase the temperature, if it's going to be breaking down by avalanche? Less time. Yeah, so mean free scattering, or the mean free path is shorter, you think? That's what I said. Okay, no. Okay. Yeah, I should read my own slide. Okay. Why does the mean free path decrease with increasing temperature? Just remember. Yeah, there's more lattice vibrations, right? So, yeah. Yeah, good question. Somebody want to explain this? Ali? Right. Okay, so let's remember, you need to have, you want the electron to lose some energy that's greater than the band gap energy whenever it collides, right? In order to generate an electron hole pair. Okay? So if the electron travels a long distance, will travel a long distance between scattering events, then that means it can go from, okay, so this is EC, let's say, right? So this is a case where you have a long mean free path before, so you have a long distance to gain kinetic energy greater than the band gap energy, okay? So this is at, let's say, low temperature. But now at higher temperature, you don't go as far, but you still have to gain something greater than, the band gap energy to avalanche. So that means now you have to actually have your, band bending much more steep, right? So the electric field 1 over Q times the band bending, the electric field has to be higher, right? Okay? So exactly, it's because the mean free path is shorter as you increase temperature that you need higher electric field. In other words, the breakdown voltage increases. Okay, so you can heat up your diode, and if it lasts to higher breakdown voltage, higher voltage before it breaks down, then you know breakdown must be occurring by avalanche. For tunneling, okay, I guess I should have drawn this up here. The breakdown voltage decreases. Okay, so let's go back to tunneling. Sorry, it's a little bit messy, but okay, so qualitatively, the rate at which carriers can tunnel will increase with temperature. So you can more easily get tunneling current to flow if you heat up the diode. That's basically it. Okay? All right, so those are, if I ask you 2 ways to distinguish the breakdown mechanism, one way is by temperature dependence, and another way is by just the magnitude of the breakdown voltage. Okay? And so here's here's a 1-page summary for this last part of the lecture. Okay? All right, yes, questions? How do you quantify the breakdown current? Oh, yeah, okay. Yeah, I didn't give you an equation, right? Okay, it's covered in the textbook PRA. Actually, I think people really don't care too much. Like, they just, lots of current, right? That's just the voltage at which lots of current flows. And actually can vary quite a bit from device to device. But so in this class, just assume it's like a vertical line going south, yeah. But yeah, if you want some equations, the problem is it's an empirical model, and then the exponential factor can vary over like a range from 3 to 6 or something. So it's all just empirically derived. Yeah. It actually has to do a little bit with the geometry of your p-n junction. So let's say, ideally you have a diode that's just n-type doped and p-type doped, and it's just like a planar device. But see, in a real integrated circuit, you also have these corners. So depending on how round or how sharp these corners are, you can actually have locally enhanced electric fields, and it'll just like break down and all this. So in reality, real devices, it's not easy to come up with a simple equation to model the current in breakdown, because it depends, because it's high electric fields usually, and then it's highly geometry dependent. Yeah. All right. Any other questions? Any questions? Any worries about the quiz coming up? It is going to be a little more difficult, but it shouldn't be longer, I don't think. But if you know the material of homeworks 4 and 5, not including p-n junction diodes, you should do well. No p-n junction diodes on the quiz. Anything else? Okay. No calculators, please. Yeah, you should not need a calculator. Yeah. Okay. All right. Great. Have a good weekend, and I'll see you on Tuesday.